So over the next few videos I want to go ahead and show you different matrix operations now that we've learned what a matrix is. And the first operation we want to learn how to do is matrix addition. So let's take a look at that. So we're looking at matrix addition here, and I think what we're going to do is let's just work an example straight off the bat. So let's go ahead and add together these two matrices. We've got the matrix A, and let's say matrix A has the entries, and it's we'll say it's a 2 by 3 matrix, and it's got the entries 1, 2, 3, 4, 5, 6, and then let's say matrix B is the matrix 7, -2, 0, 1, -5, and -6. So how do I add together A plus B? Well, it's actually sort of as you would expect. Here is the 1, 1 entry of matrix A, and we're going to add it to the 1, 1 entry of matrix B. So the first entry of the sum of these two matrices is 8, because we've added together those two entries. When we add 2 to -2, we get 0. When we add 3 to 0, we get 3. This would give us the entry 5, this would give us the entry 0, and this would give us the entry 0. So that's really all there is to matrix addition. You add like entries. So to add two matrices, we add like entries. Okay. Let's go ahead and now explore this a little more carefully here. What if you were asked to add together the matrix A equals, let's say it's 1, 2, 3, 4, this 2 by 2 matrix, right? 2 rows, 2 columns, so this is the number of rows, this is the number of columns. Remember again, those go R by C, RC. So first you list the rows, then you list the columns. And let's add to that matrix B, and let's say matrix B is the matrix that has -2, 1, 3, 5, 6, 2. Well, if you tried to add these two matrices together, what would happen? Well, if the rule for adding two matrices together is to add like entries, you'll see that these two matrices cannot be added together. How come? Because they have different dimensions. So in fact, you can only add together matrices of the same dimension. So let's go ahead and now actually define matrix addition formally, and this is how we'd say it. So we'd say, let's let A and B be matrices in the space of n by n matrices. Okay, so they both, what I'm saying here is A and B are both matrices, and they have the same dimensions. They have n rows and they have m columns. Okay, then we could represent A as this matrix that has it's really just a sequence of I times j entries with I rows, j columns. So that's the typical element sitting inside this matrix, and matrix B would look like Bij. And so then this new matrix, A plus B, well, first of all, where does it live? It lives in the same space. So it's also an n by n matrix, and its entries, its ij entry, that's the word entry, is just Aij plus Bij, meaning you add together the like entries. So I'm not expecting this notation to make what we did up here in example 1 somehow more clear. But what I do want you to do is start practicing this notation, because as we go further along into our study of vector spaces, being able to write in this sort of notation is going to be essential to being able to work with more abstract objects. So let's just make sure this all makes sense. Where do these two matrices live, A and B? They live in the space of n by n matrices with real valued coefficients. Then we can go ahead and represent this matrix A as a sequence of Aij entries, and B has this sequence, and so when we add them together, all I'm saying here is that the new ijth entry is simply the sum of the two. And the other thing that I really want to make sure we understand is these two matrices, A and B, came from this space. When we add them together, we remain in this space, and that is not going to be the case when we get to matrix multiplication. So now I want to look at some properties of matrix addition. So let's let matrix D be the matrix 1, 2, 3, 4. That means it's a 2 by 2 matrix. We'll let matrix E be the matrix 0, 1, 0, 1. And let's let matrix F be the matrix 1, 0, 0, 1. By the way, we're going to give this matrix here, matrix F, a different name as we go further along. We're eventually going to call it the identity matrix, and you'll see why that's the case when we get to matrix multiplication. Okay, so let's go ahead and add together matrix D and matrix E. Well, simply writing out the two matrices in long form, we have 1, 2, 3, 4, that matrix, plus the matrix 0, 1, 0, 1. We add together the like entries, and we end up with what matrix? Well, this would be 1. This entry would be 3. Okay, by the way, what entry is that? That's the 1, 2 entry, and this is the 1, 2 entry. So the new 1, 2 entry of the new matrix is simply the sum of those two. That helps to explain this notation that we were using above. Okay, and then we add together the remaining entries, so we get 3 and 5. So that's the sum of the two matrices. So I'm going to show you something, and it shouldn't be too surprising. What do you think we get when we add matrix E to matrix D? Well, matrix E, we said, is the matrix 0, 1, 0, 1, and matrix D was the matrix 1, 2, and 3, 4, and when we combine these together, lo and behold, not too exciting, we get the same result. So what does this mean? Okay. So I'd like to run through these properties here. We're going to say that matrix addition is commutative. Okay. Commutative means that the order in which we do the order in which we add these two matrices together doesn't matter, and we saw that by way of this example. Whether I add matrix D to matrix E or matrix E to matrix D, we get the same resulting matrix. The reason why that is because all of the entries of matrix D and all of the entries of matrix E come from the real numbers. So we're simply adding together real numbers, and the real numbers themselves are commutative. Now, you might be saying, well, what's the big deal here? And I agree. It's not very exciting to state that matrix addition is commutative. But I want you to pay attention to that and contrast that with matrix multiplication. When we start multiplying matrices together, we will learn that the order in which we multiply those two matrices actually does matter. And I can't stress that point enough. This is the first time probably in your math career where you've learned that the order in which you do multiplication matters. You know, most of the multiplication you've ever done, let's say we took 2 times 3 or 3 times 2, we always get the same answer. That will not be the case when we get to matrix multiplication. So that's why I'm stressing the properties right here when we're talking about matrix addition. Okay, so we're working with those same three matrices here. Let's say we took matrix D plus matrix E, and then we're going to add to that matrix F. Well, we've already said that matrix D plus matrix E, we've already done that. That was this result from before. So that would be 1, 3, 3, 5. And we're going to add to that matrix F, which was that identity matrix. And when we add those together, we get 2, 3, 3, 6. Okay? What I'd now like to do is let's take matrix D and let's add that to the sum of matrix E and matrix F. So what's the difference here? The difference between these two examples is the grouping symbols. Here I group together matrix D and matrix E, which by order of operations means I have to do that first, then added matrix F to the result, and here I've switched that. Okay, so let's take a look here. Matrix D was 1, 2, 3, 4, and we're adding to that the sum of matrix E, which was 0, 1, 0, 1, and matrix F, which is 1, 0, 0, 1. And I've got to put sort of an extra set of grouping symbols around these, telling me to do this matrix addition first. So that gives us 1, 2, 3, 4 for matrix D, plus adding these two matrices together, we get the entries 1, 1, 0, 2. Double check me, did I add those correctly? Yep, I think I did. Okay, so now we combine these two matrices and we get 2, 3, 3, 6. So again, notice that we got the same answer regardless of the grouping symbols. So now we can say that matrix addition is associative. Remember that the associative property says that it doesn't matter in which we first, it doesn't matter the order. If we're adding together several entities, it doesn't matter the order in which we grab two of them to add and then add the third to it. Now notice one thing that didn't happen is I didn't interchange D, E, and F. I just simply changed which of the two I added together first. So commutativity, what we looked at before, says we can interchange the order. Associativity says we can interchange the grouping symbols. Okay, I have one more thing I want to show you, and that is the additive identity matrix. So we're going to let 0 with a bar over it with n by m, that's a 0, denote the additive identity of the space of n by n matrices with real valued entries. Okay? So what does that matrix look like? Well, it's the matrix where each ij entry is 0. So the 0 matrix, let's say of the 2 by 3 space of matrices, let's see here. So we have the 0 matrix of the 2 by 3 space of matrices. What would that look like? Well, it would look like 0, 0, 0, 0, 0, 0. Each of the entries here are 0. So whenever you see this 0 matrix, just to save us having to write out the entire matrix, it's we just name it with a 0 with a line over the top. That's how we know it's a matrix. And then we say 2 by 3. That gives us the dimensions of that 0 matrix. And I'm not going to prove this to you. It's easy to prove, so you can take a look at it on your own. But notice that if we take the 0 of the n by n matrix and add it to some other n by n matrix, we're just going to end up with that original n by n matrix. And in fact, that's the same as if we had taken it and interchanged the order n by m plus 0. By m. So this says that just like with real numbers, when you're learning how to do regular addition, you can add together 3 and 2, or you can add together 5 and 7. There's a number, namely 0, that when we add it to the first number, it doesn't change it. The same thing is true with matrix addition. And so this is called the, let's just underline that, this is called the additive identity. Okay, we're going to keep going in the next videos.